Welcome back. Let's put things in perspective. We have been talking about classical statistical mechanics, basically the formalism that is required to treat systems classically, and we have looked at a number of examples, starting with a classical ideal gas, collection of spins in a magnetic field, or there are these harmonic oscillators which actually make up a nice model for solids which give you right kind of specific heat. Though we haven't seen that yet, we have done some calculations on that. Whatever has been discussed so far, they all are on the presumption that the temperature is high, and we are really in the classical domain when the thermal fluctuations dominate over the quantum energy scales. And we are coming slowly close to that, and we will be taking on quantum stat mech from next class onwards. But let us first do some examples of the grand canonical ensemble, and then we will go on to discuss applications of that, and talk about photon gas, talk about its equipartition theorem and virial theorem, and we will do some problems on entropy and canonical distribution. Then we will do mixing of gases, which gives rise to a paradox which is known as Gibbs paradox, and this needs to be resolved, and we will sort of see all of them one after another. So, we have been doing grand canonical, ensemble, and how does it differ from the canonical ensemble? We have said that number of particles is not a measurable quantity. So, let us relax the condition that the members of the ensemble cannot exchange number of particles. So, in addition to energy, they also exchange the number of particles, and in this process they would come to an equilibrium temperature T and an equilibrium chemical potential mu. So, this is the idea of grand canonical ensemble, and we have written down the partition function of that in the last class, which is equal to there is a summation over say R and S. We are knowingly intentionally we are using these two indices for to differentiate between the particle number index and the energy index, and this is equal to an exponential minus alpha nr minus beta es. So, this is what was written down earlier, and alpha and beta were identified as mu over kt, and beta is 1 over kt. So, this is the definition of the grand canonical partition function. So, and to distinguish it from the canonical partition function, we write it with a capital G. G stands for grand canonical, and if you do a little more simplification of that, this really looks like it is equal to sum over nr equal to 0 to infinity, and there is an exponential beta mu nr, that is the first term, and this then it is s exponential minus beta es. So, I just factorize the let me write this bracket here and a bracket here and so on. So, we just factorize this exponential and write it in this form, but this gives us a nice handle over it, where we can write it as a sum nr equal to 0 to infinity exponential. So, we will write this exponential beta mu as a quantity called as zf, zf to the power nr, and then is the same canonical partition function, which is at a given t and n, or you can write it as a beta and n. Okay. So, this part is the canonical partition function which we have seen earlier, and this part is written as a zf to the power n, and this zf is called as the fugacity. fugacity of the system, and this is equal to exponential beta mu. We will use this fugacity extensively when we talk about Bose-Einstein condensates and so on. So, right now the canonical partition function nicely factorizes into a sum over the number of particles, which is nr going from 0 to infinity, and also the canonical part that we have dealt before. So, then this Zg can be also written as it is this step itself, it is equal to sum over nr exponential beta mu nr plus a log of z. Well, in the sense that you can let us not, so we can also write it as log of z, and there is a sum over nr from 0 to infinity. There are various ways of writing the grand canonical partition function, but what our idea is that if we can find out the canonical partition function, which we have seen in a number of cases how to calculate that, then getting the grand canonical is not that difficult. Okay. So, because this partition function Zg can be represented in terms of the canonical partition function. Okay. Now, let me remind you that the distribution that we are talking about is indeed a sharp distribution, which is peaked at some value of energy and a value of number of particles. So, this sum over nr from 0 to infinity can be replaced by, this sum can be replaced by the largest term in the sum. And this is possible because we know that we are dealing very close to the microcanonical distribution, which talks about a particular number of particles and particular energy, and here also that we are just talking about if this grand canonical is very close to the microcanonical, then we should be talking about the distribution peaking at some number of particles, and so this can be replaced, this sum can be replaced by the largest term in the sum. So, what I mean is that if you have terms which are very small, so a large number of terms which are like these are very small number of terms, and then something very large. So, the sum is dominated by this large term. So, in that spirit we can write down this Zg as nothing but it is equal to exponential. Now, this sum goes away and we have a minus beta and we have minus k log z and a minus mu n, and so now my sum goes away and we have taken that this is the largest term in the sum. Okay. So, now this quantity is called as a grand potential. So, phi is called as the grand potential. Which is in line with this Helmholtz free energy, because you have seen that this is actually you take the log of the partition function and you get it as the free energy, the Helmholtz free energy. So, this is equal to e to the power minus beta phi, and that is a sort of form of the grand canonical partition function. So, what is it good at? It is sort of good at a number of things, that is we can get the free energies. So, we write this phi as which is a function of t, v and mu. Remember that it is not a function of n anymore because n is not constant. So, this is equal to f t v n minus of mu n, which is nothing but equal to minus p v. So, you see that here it is this k log z, and there is a multiplied by a beta, that will give you this f, and then f will, and f minus mu n gives you the grand potential. So, this is equal to nothing but equal to, so I will still write these dependencies explicitly. So, this is equal to minus k t log of z g, and this is a T v mu, and in a continuum notation, of course, you have a z g, this is equal to h to the power 3 n n factorial and a d cube 3 n q d cube 3 n p and e to the power minus beta. Now, h minus mu n is what you have to consider. So, h is the Hamiltonian of the system. And now, instead of the Hamiltonian, you have to take the h minus mu n because of this families of the ensembles being able to exchange the number of particles there. Okay. So, and from there you can again get this various quantities such as entropy here is equal to minus del phi del t at a given v mu. Remember, S was minus del f del t at a v n, now it is a v mu at a constant v mu. Pressure is again given by minus del phi del v t mu, and the number of particles is given by del phi del mu and t v. Okay. So, these are the thermodynamic quantities that you can obtain from the grand canonical partition function, and these are, as you know, these are useful for deriving various things, including the equation of state and various other physical things such as magnetization, such as susceptibility, or such as specific heat, and so on and so forth. Okay. So, this is where we stand at this moment, and we can also extend this and calculate the fluctuations in the number of particles. I mean fluctuation in energy and so on, and then we can use this as Zg. We can write it in terms of beta, and that is T n n or mu, but we can also write it in terms of the fugacity, which is which contains beta mu. So, this is equal to nothing but this n r equal to 0 to infinity. We go back to our summation, and this is equal to n r equal to 0 to infinity, and z f to the power n r, and we have a canonical partition function which is given by T n or beta n. So, average energy can be expressed as 1 over j z g, which is the normalization factor, and E s z f to the power n r and exponential minus beta E s. I write it explicitly here, and this is nothing but minus of del del beta log of z g, and you have a beta and z f. Okay. This was exactly the same relation as we have seen earlier, excepting that the number of or the fluctuation in energy was simply minus del del beta of log of z, where z was a canonical partition function. Now, we write it in terms of the grand canonical partition function. So, let us look at the fluctuation in the number of particles. and this is again that nr, or rather we are finding out. So, it is a fluctuation of energy. What I mean is that then you can calculate ES square average and calculate what is delta ES say by ES and so on, which is nothing but ES square average minus ES average square divided by ES, and so there is a root over of that and so on. So, this gives you the fluctuation. All these have been shown earlier. We are just showing you how to express the average quantity again in terms of the this distribution. So, NR is average NR is nothing but 1 over ZG summation over R, and then there is a NR ZF to the power NR exponential minus beta ES, which can be simplified in the form of del ZF log of a ZG and beta and ZF. Okay. So, this is the average number of particles, and again one can calculate the relative fluctuation in the number of particles as this, which is equal to NR square average minus NR average square divided by NR average, and NR square average, you know how to calculate it. You take a double derivative with respect to the fugacity here of the grand canonical partition function. Similarly, you can also calculate how to get this ES square average, and which is taking a double derivative with respect to beta. Okay. So, these are the average quantities, and if you really want to know the number fluctuations, that can be obtained, and which is simply equal to NR square average minus NR average square, and this is equal to 1 over beta square del mu. Let me write it in the next page. Delta n square, this is equal to 1 by beta square del mu. These are different ways of writing it, but they mean the same thing, log of ZG. You can also take a derivative with respect to fugacity, and this is equal to 1 over beta, and then there is del NR, which is the average number of particles at a given T and V, which is nothing but 1 over beta del n del mu T V. Okay. And it is easy to understand that delta n square, this fluctuation square is positive, and again this square of these quantity that sort of vanishes in the thermodynamic limit, which gives you a justification of using statistical mechanics reliably to a large number of copies of the system, or when the number of data points are high, it makes sense to use statistical analysis of the system. Okay. So, let us go to another thing and talk about as an example of this. Let us talk about quantity, or rather let us talk about a system called as a photon gas. And why we are discussing it now? We have not discussed a photon gas earlier, even within classical mechanics. We have only talked about classical ideal gas. So, a classical ideal gas, as said several times, the energy is given by P square over 2m, okay? Or you can write a Pi square and then sum over I. You can keep a Mi as well, just to make this masses of the particles to be different. Now, we have a different dispersion, and let us just write it from one particle. We have a dispersion which is like for the relativistic dispersion, which is a P square C square plus some m naught square C4, where m naught is the the rest mass of the system. And let me just write it as m here, just to bring various limits into the picture, and this is a relativistic dispersion. Okay. So, when you take the ultra relativistic limit, so this mc square is of the order of 0.5 MeV, whereas this can be arbitrarily large, the first term can be arbitrarily large. So, E can be written as Pc, okay. And this is called as the ultra relativistic dispersion, or this is the dispersion of the photon gas. And it also makes sense because photons are known to be massless particles. Okay. We will talk about the rest mass when it comes. Right now, I just left it as m. So, this is a dispersion that we want to talk about. And how is it different than the classical ideal gas? There is a p square dispersion where there is a linear in p dispersion. So, there is a linear dispersion such as so p square looks like a parabola E versus p, and this really looks like a sort of linear dispersion, and we have the dispersion is this when we just write it as something like this. Okay. So, we so E versus p, and the slope is given by c, which is assumably the speed of light. Okay. So, for a photon gas, first discuss the chemical potential of a photon gas is 0. Okay. So, that means that all these mu that we have been talking about, mu is equal to 0, identically equal to 0 for a photon gas, and then we can basically there is no difference between the canonical and the grand canonical partition function, because we are we have put mu equal to 0. So, as if there is no need for that consideration of the mu. And the reason for this is that if you keep the photon gas inside a container, so there is a photon gas, there is a container there made of anything, and there is a photon gas. And if you remember Planck's theory, Planck just said that the container will exchange photons with the surrounding in packets of h nu or h cross omega, and so you cannot keep the particle number to be constant if you keep a photon gas inside a container. Okay. So, there is no way to keep photon number constant. So, if you wish to relate to what we have done, so we have this system and there is this system A, and there is A prime, and then there is a 0, and we have always considered A 0 to be isolated. So, even if A exchanges energy and the number of particles with A prime, A 0 is still insulated, that is, it does not talk to the surroundings, but here you cannot do that. So, we really do not have a constraint n I equal to n sum over all I. This constraint is no longer there for the photon gas. Okay. So, if this constraint is not there, then of course, when you try minimizing this distribution, just to remind you, that we minimize this distribution, which is sum over r n r, and wanted to find that at what value of n I, we have called it as n I star, that this distribution peaks, but subjected to a condition that sum over n I equal to n. And this really needed us to have Lagrange's antideterminant multiplier, which is equal to mu or mu over k t. Okay. So, if this condition is not there, then mu is identically equal to 0. Okay. And this condition is it becomes a defunct condition, then we do not need a Lagrange's antideterminant multiplier. So, mu equal to 0 for a photon gas. Let us do some more analysis of the photon gas, and the dispersion of a photon gas is, as I wrote earlier, dispersion means E versus K relation or E versus P relation. So, this is equal to P and C. Okay. So, the rest mass energy is 0, and in any case what is called as the ultra relativistic limit, even when the mass is not equal to 0, you can arbitrarily accelerate it at very large energies when this 0.5 MeV does not compare with the P c term or the P square c square term. Okay. So, we can write down the partition function as Z is equal to V over H cube and a minus infinity to plus infinity e to the power minus beta P c. We simply write it as P c because we have taken the minus infinity to plus infinity. So, the mod is taken care of, and we have say for example, a d cube P, and this is whole to the power n, because these are non-interacting photons. Okay. The photons are not interacting among themselves. So, we can calculate the one particle partition function and raise it to the power n. Okay. So, Z1 can be written as a V over H cube, and we try to perform this integral, and the easiest way is to do it instead of doing a minus infinity to plus infinity. If we convert it into a spherical integral, that is going to be easier, and in that case you have a 0 to infinity and you have a exponential minus beta P c and a P square dP. I hope you understand this. This is nothing but this beta E, okay, and which is the weighting factor, and then it is integrated over all P, and the Q integral has already been done, and that is how we got a V, and V to the power n for all n particles. Okay. So, that tells you, because this dispersion does not depend upon the positional coordinates. So, the V can be easily integrated over, and we land up with an integral like this, and this integral has a simple form. I mean, this is called as a gamma function integral. And this is equal to, the gamma function integral is equal to some 0 to infinity x to the power n e to the power minus alpha x dx. This is equal to a gamma of n, this is written as gamma. So, gamma of n divided by alpha to the power n plus 1, and in general gamma of n is defined as this x to the power n minus 1 0 to infinity and e to the power minus x dx. Okay. So, this is a gamma function integral, and it can be easily performed, and one gets Z1 is equal to V over H cube, and we have a 8 pi, and then we have a kT over C whole cube, and C is the, of course, the speed of light. Speed of photons, and you know light is nothing but the quanta of light is photons. So, these are speed of light, okay, or speed of photons. Okay. So, once we calculate Z1, we can raise it to the power n to get the full partition function, and once we get the full partition function, it is easy to calculate various other quantities, and that is what we are going to do here. So, we calculate the free energy. And free energy is equal to minus k T log z, which is z is equal to z1 to the power n. Okay, so, this is equal to minus n k T and a log of 8 pi k square v by h cube c cube n, and we have a T cube. Okay. So, this is the free energy of the photon gas, and we can also calculate the pressure, which is equal to minus del F del V, and this is at a given T and N, and this is equal to n k T ddV of log of V, and this gives you n k T over V. Remember, we are using still this capital N, which is the total number of photons. So, even if it exchanges, we still are talking about, I mean, the container exchanges the particles or the photons with the surrounding, but we are still talking about the total number of photons, and this gives us a PV equal to n k T. This is an interesting result because same equation of state as non-relativistic case. Okay. However, there is something that is different that you will see here is when we talk about the internal energy, or rather this internal energy that is given by u equal to minus del del beta of log z, which we have derived earlier, it is equal to 3 n k T, and this is different than the non-relativistic case. I will write it in short, okay, because this was 3 n by 2 k T with only one harmonic degree of freedom, which is p square over 2 m. But here we have a relativistic dispersion, which is P c, and the internal energy is like what we get for the harmonic oscillator, where there are two harmonic degrees of freedom. Here of course, there is no harmonic degree of freedom, but we get a internal energy which is twice of that in the relativistic case. And similarly, we can get other quantities such as enthalpy, it is equal to u plus P v, which is equal to 3 n k T, and P v is derived earlier, which is n k T, and this is equal to this is 4 n k T, and this enthalpy is also different. Presumably, it's easy to understand that it's 3 by 2 for the non-relativistic case, and then you still have n k T. So, it's 1 half plus 1, which is 5 by 2 n k T, whereas it's 4 n k T. Okay. So, we do not see any harmonic degrees of freedom. So, really the defining equipartition theorem is a difficulty here, but what we still can do is that we can do a virial. So, virial of photon gas. So, it is not really an equipartition theorem, but we are just talking about a virial. And how do we define a virial? So, we define it by this symbol, which is some calligraphic form of V, and this is the expectation value or the average value of I equal to 1 to 3, and a P I q I dot. Okay. And say this is given to be equal to 3 k T. However, we have derived it that this independent of any kind of system that we are talking about, this P I q I dot equal to 3 k T. Okay. And if you take it over n particles, n non-interacting particles, then it will be 3 n k T. Okay. So, now let us calculate quote unquote the equipartition theorem. Because the way we have defined equipartition theorem, it should not be valid here, but we can still talk about average energy or the internal energy of the system, which should be same as what the equipartition theorem finally gives. Okay. So, obtain equipartition theorem. For the photon gas. That is the question, and in order to do that, we simply take the virial, and you see the virial is actually nothing but P dot u, where u is the velocity, which is equal to 3 k T. Now, I just remind you that the magnitude of velocity in relativistic mechanics is given by 1 minus u divided by u into this gamma factor, where gamma is equal to 1 by root over 1 minus u square by c square. So, that tells us that P dot u is really a m 0 u. Now, I go back to my notation of the rest mass. So, this m 0 u and u divided by root over 1 minus u square by c square, and this is nothing but equal to m 0 u square and root over of 1 minus u square by c square. So, what you see inside the virial, that is inside the average value, is nothing but equal to P dot u, which is nothing but equal to m 0 u square divided by 1 minus u square by c square, m 0 being the rest mass of the system and u being the velocity of the particle. Okay. And so, that tells you the virial theorem gives this m 0 u square, just doing it for one particle, 1 minus u square by c square, this is equal to 3 k T, or you can write it in a compact fashion as m 0 u square gamma equal to 3 k T. Okay. And gamma equal to 1 divided by 1 minus u square by c square. That is the velocity transformation formula that we have used. Now, let us look at the extreme relativistic limit, that is E equal to P c. Okay. So, this is m c square. So, gamma m 0 u square. So, what I mean is that u tending to c. So, that gives you m c square is equal to 3 k T, where m is equal to gamma m 0. Okay, and this gamma is tending to 1, because u by c is u tending to c, u square by c square will be equal to 1. So, this is, I mean, gamma tending to 1 means that inverse of this. So, this is equal to the total energy of the system in the extreme relativistic limit, and the average value of that equal to 3 k T. So, this is the equipartition theorem that we have. Okay. And for the other limit, that is the non-relativistic limit, we have this as half, I mean, m naught u square. this is equal to 3 by 2 kT. This result we know, and here of course, the only mass that remains is this m0, which is different than m. It's not being renormalized by the gamma factor, but this is it's equal to 3 by 2 kT, a known result. This is equipartition theorem and a known result. This is for relativistic case or ultra relativistic case, and this for non-relativistic case. Okay, so and they correspond to different dispersion. We have a dispersion which is equal to linear in P, and we have a dispersion in the second case as this is in quadratic in P, and this is how the difference arises. Okay. All right. So, let us do an example which is important in this in the whole the context that we have been talking about, and the example is that we are talking about entropy. Okay. And you have been looking at this Lagrange's undetermined multiplier. So, this example will try to make this thing clear that what exactly is this undetermined multiplier, and the kind of expression that we are using for entropy, is that a good expression. So, or rather how useful it is. Of course, it is a correct expression. So, we have used it as R and a PR log of PR. This has been used earlier. So, the form of PR that which makes the entropy maximum is the one that gives you a canonical distribution. Okay. So, I will tell you the form of PR, that is makes the S maximum, that is entropy maximum, with a mean energy E this follows a canonical distribution, and we have actually derived this, but this is going to make things further clear that this distribution, which is nothing but a Boltzmann distribution, which is exponential minus beta ER divided by sum over R exponential minus beta ER, that PR really enters into this problem. Okay. And how do we actually see this? How do we convince ourselves that this is the entropy? This the PR in the entropy actually corresponds to the canonical distribution, and this makes the entropy to be maximum and with a mean energy E. Okay. So, we have these constraint conditions as so we have a RPR equal to 1. So, this is one constraint condition, and we also have R, you have a ERPR that's equal to E, that's a second constraint condition, one which is equal to a constant, and this is the second constraint condition. Okay. So, what we try to do is that we try to maximize the entropy. Okay. And how do we do that? So, basically we take a delta of S, which is which gives you a extremum of this, and then there is a sum over R, and then we have this K P R log PR plus a lambda 1 ERPR plus a lambda 2 PR, and this we shall put equal to 0. Okay. So, what we mean here is that we change PR to PR plus delta PR, and we see what happens to the S, that is the entropy of the system. Okay. So, we change the distribution a little from its original form, that is the Boltzmann distribution, and we try to see that what happens. So, delta of S is equal to minus K PS plus delta PS log of, or we write it as natural log. So, that is best to continue. So, this what we mean is R. So, PR plus delta PR log of PR plus delta PR and plus lambda 1 ER of PR plus delta PR plus lambda 2 PR plus delta PR. Okay. Now, you see we can neglect this term inside the log, because log makes a large number small. So, if you take a 10 to the power 6 and take a log of that number base 10, you just get a 6. So, a billion becomes just a small number, and hence inside the log, if there is a small number, that can be easily neglected. So, this is equal to S0, which is simply PR log PR plus sum over R, and then we have a minus K log of PR and K plus a lambda ER plus a lambda 2 and then delta PR, and this can be put equal to 0, okay, for extremizing it. Now, S0 is the one that is with this PR, and this is the one that came due to change in PR from PR to delta PR. Okay. So, in order for this equation to be valid, or rather, I mean there are of course other terms which are of the order of PR square, which we neglect. And we simply put this this coefficient equal to 0. So, that gives you a PR. This is equal to exponential lambda 1 over K ER and plus lambda 2 over K minus 1. So, this is what we get by putting this bracket equal to 0. So, this bracket equal to 0, okay, because S0 is not equal to 0. So, for minimizing, that is so actually if you write it delta S, this S0 is just a constant, okay. I mean so S0 is the original entropy of this system when you have not done this PR to PR plus delta PR. The only thing that comes to the first order in PR is this this term with this bracket into delta PR. So, we are just putting the coefficient of this delta PR term equal to 0, and this is what we get by doing that. Now, we have to determine delta 1 and delta 2, lambda 1 and lambda 2. This is not delta 1 and delta 2, these are lambda 1 and lambda 2 that we want to calculate. Now, the two observations are important here. Since ER is unbounded, it is necessary to have lambda 1 to be negative, okay. And why is that? That is because you can have otherwise this probability will diverge, and in a general case ER can go from 0 to infinity or from minus infinity to plus infinity. So, we have to keep this lambda 1 to be negative in order for these PR to have physically meaningful values, because it is anyway the probability cannot go to infinity for ER to go to infinity. So, the lambda 1 needs to be negative. All right. So, this we need because you have PR to be equal to 1, you have to satisfy this. So, we write just to satisfy, all right. And of course, also ER, PR to converge, all right. So, if we write then lambda 1 over k, which is this term in the first term inside the square bracket, that is inside the argument or rather the argument of the exponential, this you write it as minus beta, understanding that beta is greater than 0. So, we get 1 equal to sum over r, PR equal to e to the power lambda 2 by k minus 1, and then there is a r e to the power minus beta ER. Okay. So, this is nothing but e to the power lambda 2 by k. So, this is e to the power lambda 2 by k minus 1. This minus 1 is actually here, okay, and this is there, and then there is a z of beta. Okay. So, this is what we get for the equation by extremizing the entropy, and if you put it in this equation number, let us call it as equation number 1, let us call it as equation number 1. If you put it there, then we get exactly what we get as the canonical distribution. So, we get a PR equal to exponential minus beta ER divided by this z of beta, which is the canonical partition function. So, which means that this distribution really extremizes or maximizes the entropy with a mean energy of E. Okay. Okay. So, let us go on to another topic, rather a subtopic, which in some sense has been told to you, but however, do some small calculation, and this calculation will get us closer to this quantum mechanical case, and which is something that we are going to start on the next day onwards. So, this topic is called the mixing of two gases. And which gives rise to what is called as the Gibbs paradox. Okay. So, we just remind you, we derived this earlier, the entropy of an ideal monatomic gas is S is equal to N k log of V divided by H cube, and we have a 4 pi me divided by 3 n whole to the power 3 by 2 to the power n plus 3 by 2 n k. Okay. This has been derived earlier for the ideal monatomic gas. Okay. There is a problem with this expression, and which is what the main reason for this Gibbs paradox to occur, okay, and we will talk about that in just a while. Now, think about a thought experiment. Okay. A thought experiment is the experiment that you perform in your mind, and you take a container, okay, and which has a removable partition. Okay. This partition, you can remove it at your own will. And let us say that you have kept a gas A and a gas B, which are distinct, which are different, say nitrogen and helium or some other gas, I mean the two different gases, and we have this as N1 V1 T and N2 V2 T, and so they are maintained at the same temperature, but the number of particles and the volume of this are different, and if you want we can move this partition little on one side, so that you know that the volumes are different. So, the thought experiment is to remove the partition and let the gases mix. So, what will happen to the entropy is what we want to understand. Okay. So, we need to check change in entropy. So, that is the question that we ask, that what will happen. So, before mixing, the entropy is just additive. So, entropy will add up and we write Si, where I equal to 1, 2. This is equal to Ni k log of Vi by h cube 2 m k t by 3 by 2 plus 3 by 2 Ni k and so on. Okay. So, for both the gases, and so this is written a little in a simpler form, is k log of Vi plus 3 by 2 Ni k log of 2, you can have a Mi here because they are two different gases, 2 pi Mi k t by h square plus 1 and so on. So, many books will actually introduce a thermal de Broglie wavelength, which is defined as root over 2 pi m k t. You can see that this 2 pi m k t comes here and so on. So, this you can write it in terms of that as well, okay, this thermal de Broglie wavelength. So, after mixing, okay. So, these are individual gases and they would be summed over, and after mixing one has SF, this is equal to this I equal to 1 to 2. If you want, you can write it initial because this I and this I initial, they are not the same. So, S final is I equal to 1 to 2, and we have a Ni k log V. So, you remove the partition and this thing becomes simply like 1, the partition is completely removed and you have a plus B gas, and we have a N1 plus N2 number of particles, V1 plus V2 volume, and the temperature still remains as T. Okay. So, so this is equal to Ni k log V plus a 3 by 2 Ni k log of 2 pi m I k t by h square plus 1, and that is a final entropy, and where V is equal to V1 plus V2. Okay. So, let us define the entropy of mixing. And the entropy of mixing is given as SF minus Si, which is equal to k N1 log of V by V1 plus N2 log of V by V2. So, this expression becomes very simple if you sort of subtract the final and the initial entropies of the system. So, we write SF S final minus S initial. As the total volume V is greater than V1 and V2, you can check that delta S is always 0, and this is what is expected, that you do some do some process, and this process is gives rise to a rise in entropy, and that is very clear because your log of this V by V1 is actually larger than 1. This ratio, both the ratios are larger than 1. So, this delta S should be greater than 0. Okay. Now, the second thought experiment. So, now, this let me write it as first thought experiment. First thought experiment. Okay. And in the next thought experiment, or the second thought experiment, what we do is that we have this gas which is the same gas A and A. And then you have the masses of the particles are same, and you remove the partition and let the gases mix, and we should get similar results because we now have your delta S should still be greater than 0, and the only difference that you have here is Mi is equal to Mf. So, same gas allowed to mix. So, both of them say nitrogen, and then this process should be completely reversible, and in a reversible process the change in entropy should be 0, and but this calculation gives the entropy to be non-zero, and it is again positive, and there is a very simple form for that. So, let us write that in just a moment. So, we assume that M1 is equal to M2 equal to some M. So, the final entropy is equal to some Nk log V, V is again V1 plus V2 and N is N1 plus N2. It is 3 by 2 Nk and log of 2 pi m Kt divided by h square plus 1, and N is equal to N1 plus N2. V is equal to V1 plus V2. Okay. Again, delta S is greater than 0, okay, but which should not be. So, this is counterintuitive because you are mixing the same gas. Okay. So, this process should be reversible. So, if you put back the partition, there should be no change, and this perfectly reversible process, but this calculation gives you this thing to be the change in entropy to be equal to 0. So, what is this change in entropy? You can write it in a particularly simple fashion, and this becomes equal to Kn I equal to 1 to 2 xi log of xi, where x1 is equal to n1 divided by n1 plus n2, which is nothing but V1 equal to V1 plus V2, and this x2 is equal to it can be simplified, this delta S, which is the entropy of mixing, can be simplified like this. So, it is V2 divided by V1 plus V2. So, it can be written as this xi log xi, and therefore, both the terms. So, if you have n1 equal to n2 and V1 equal to V2, so x1 equal to, just for a special case, let us take n1 and n1 equal to n2 and V1 equal to V2. So, x1 equal to x2 equal to half, and that tells us that delta S, which is equal to minus Kn half log half plus a half log half, and that tells you that this is equal to nothing but Nk log 2, okay. And this should have been 0 because this is the same gas of equal proportion, equal volume, and you have first mixed them, or you have put a partition, they would just give no difference in the entropy of mixing should be 0, but it is not true At least as far as this calculation goes, it gives you a result which is n k log 2. Log 2 has a value, say for example 0.693, n depends on n is the number of particles and k is the Boltzmann constant. So, we need to resolve this, and so this is called a paradox, because the calculations give something and we are unable to find anything wrong in that argument, but physically if we try to understand the problem, it definitely looks like that for a completely reversible system you get an entropy to be equal to non-zero or greater than 0 here. The problem lies with this expression that we have started with, this expression that we have started with. So, this expression, let me write it with some color, and this expression is actually wrong. Okay. And let us see how this is wrong, even though we have derived this from the first principles, that is we have calculated the number of microstates, or we can go and do it using thermodynamics. We have done that, and this really gave us this result that we got here. Why it is wrong is that the expression for entropy disobeys, that is, it does not obey extensiveness. And what is extensiveness? Extensiveness is that when you double the number of particles, double the volume, and say double the energy, everything that is associated with the entropy will also double. What I mean is that if you have S which is alpha n, alpha v and alpha e, which are the intensive parameters. So, we double all of them, and then we have this S n v e. This is a relation that entropy should follow, okay, where alpha is the factor, just like I told double. So, alpha is any factor. So, if you increase it 10 times, we should have a factor of 10 in front when we have made all these quantities n, v and e 10 times larger. Okay. So, that would tell us that if we apply it to that equation of entropy that we had shown, then alpha n, alpha v and alpha e, this gives you a alpha n k and a log of alpha v by h cube 4 pi 4 pi m pi alpha e divided by 3 alpha n 3 by 2 plus 3 by 2 n alpha n k. Just check whether everything is correct in this equation by comparing it with this expression that you see here, which I have marked as wrong. And why it is wrong, you can understand it here, right here, that if you do that, then this is it becomes equal to, you cannot write it rather equal to alpha s of n e v. So, the basic premise that the entropy is an extensive quantity is violated in this expression, and there must be a fundamental reason for us to get the wrong result, even if we have done everything correct, starting with the thermodynamic derivation of this entropy. And that answer I will give just a little later, but let me show you that this can be fixed, this paradox can be fixed. And how do we fix this paradox? That we divide volume v inside the logarithm, that is inside this logarithm, that is log term, ln term, by n factorial. Okay. So, if you fix this, then Gibbs paradox is ad hocly fixed. So, ad hocly means it is not a right way of fixing something. There must be a nice first principle argument leading to this fixing of the paradox, but then we do not do that. What we do is we simply inside the logarithm term we replace it, or rather then divide it by n factorial, and then of course use all these Stirling formula etcetera in order to get this relation. So, this would fix that S of alpha E alpha V alpha n is equal to S of E V and n, alpha S of E V and n. Okay, so, this is obtained, and then you know the extensiveness of entropy is justified. Okay. All right. So, now how do you convince yourself this n factorial? If you have done these problems of permutation and combination, then you have seen that often you know you have to divide all these this counting by this n factorial, and this is in the same spirit that you do it. But anyway, it is a hand waving way of doing it. The real reason lies in indistinguishability of particles, and this will bring us to quantum mechanics. And this indistinguishability is not a feature of classical mechanics, it has to come from quantum mechanics. So, when we deal with a gas, even if it is ideal gas non-interacting, we should enforce this condition that the particles are indistinguishable. They are not labeled by 1, 2, 3, 4. We do not know any particular label attached to a particle, neither they are colored so that we can say that it is a red particle or a blue particle and so on. So, this indistinguishability has to come from quantum physics, and this leads us to the quantum stat mech. Okay. So, we are closing the discussion for the classical stat mech done so far. So, we have done thermodynamics, then we have done classical statistical mechanics. We have seen these 3 distributions, we have done a number of example problems, and now we at the end we give a very simple example of mixing of 2 gases, and found that if these 2 gases are completely identical, then the change in entropy has to vanish, which it is not. So, which means that we have made a mistake somewhere, and the mistake is deep rooted. We need to be considerate to treat these particles as indistinguishable particles, and this gives rise to 2 kinds of particles that would you know arise, called as the bosons and fermions, depending on the statistics they follow. Okay. So, this exchange statistics is something that we need to understand, and there are in fact even more than this. There are particles which follow neither boson statistics or Fermi statistics, and they are also important and becoming more and more relevant in the study of condensed matter physics and other subjects. So, we will stop here and carry on with introduction of quantum mechanical statistics from next class onwards. Thank you.